experiment?
Hey y'all, Einstein here.
Yeah.
Some of y'all may know me as the father of relativity. And relativity is the idea that space and time are connected. So one way we can prove that relativity is real is by seeing how gravity bends light. So one such example is, imagine there is a star very far away from us behind the sun, and the light coming from it bends due to the gravitational potential from the sun, and to us it seems that it is at a distance that is very different from where it is in the actual sky. And I predict that this deflection angle is twice that Newton's old physics predicted. Y'all got that?
So you might be wondering, if Einstein was such an important figure in relativity, why is it called the Eddington experiment? Well, Eddington was a British astronomer and physicist born in 1882. He was well known for his work in stellar astronomy and relativity.
The experiment was split into two teams. Eddington and his partner went to the island of Recife in Africa. The other team went to Sobral, Brazil. The eclipse and observations took place on May 29, 1919.
So Edison and his company measured the deflection angle in two different locations. This is important so that we know this is actually due to the sun's gravity and not due to any other factors. So in Sobral, they measured it to be 1.98 plus or minus 0.12 arc seconds, and then in Principe, they measured it to be 1.61 plus or minus 0.3 arc seconds. Now this is more consistent with Einstein's theory. However, we notice that there are very large uncertainties. This is really important because it's some of the first empirical evidence that supports general relativity.
As my colleague said, Eddington's experiment had very high errors. Because of this, in 1922, the experiment was repeated by a scientist named William Campbell in Australia. It has been repeated many more times since then, including 1973, where scientists from the University of Texas, including Bryce and Cecile DeWitt and Richard Matzner, traveled to the Sahara Desert to perform the same experiment. They were able to verify Einstein's theory of relativity with 3 times more accurate measurements than Eddington originally did. This meant that they only had errors of around 10% as opposed to 30%. This was especially impressive because they had to only 6 minutes to look at the eclipse as a sandstorm covered the eclipse for the rest of the time they were there. Since Eddington's time, there have been many other experiments done to prove Einstein's theory of general relativity. In 2011, UT's Donald Wingett discovered indirect evidence for gravitational waves from a binary white dwarf system. More recently, LIGO has been used to directly detect these gravitational waves from the mergers of supermassive objects like black holes and neutron stars.
During the eclipse, the sun crossed in front of a star cluster known as the Hyades. Using images, Eddington and his team compared the well-known position of the cluster with the position calculated during the eclipse. Any changes could then be measured and attributed to the sun's gravity.
We then interviewed Dr. Matzner, who redid the experiment in the Sahara Desert and gave us his perspective. He told us that his experience was very different compared to Eddington, and I quote, "Our experience was much more suited to retest Einstein's theory. We built a hut in the Sahara which had AC and cooling, keeping our photographic plates much more stable. Eddington didn't have this luxury. Also, our eclipse lasted much longer, so we were able to measure many more stars, which allowed us to increase our accuracy. So I would say our experience overall was much more different compared to Eddington, but gave us results passing expectation and accuracy, proving the theory we were set out to prove and recreate.